I can stay down here.
Yeah.
Thank you very much. And thank you. Can we give another round of applause to our amazing musician? I was a little bit baffled, but flattered when I was invited to give this talk. I'd been to Ute Lee's talk a few months ago, and I could see why someone who has really interesting ideas about home and treasure and urban planning had something to say about creativity. But I'm a mathematician, so I'm just a guy who likes shapes and numbers. And I don't really know how to talk about anything other than shapes and numbers. In fact, no mathematician does, which is why we're such fun at parties, right? So what I'm going to do is I'm going to talk a little bit about shapes and numbers. And hopefully in the end, we'll talk a little bit about simplicity and about creativity as well. I want to start with a shape. Oh, okay, that's the talk. I want to start with a shape. So picture a circle, an actual circle, anywhere in the universe. So it could be a circle around your finger, like a ring. It could be a ring around Saturn. It could be the equator. Any actual physical circle will do, and maybe we'll get some ideas from you all as well. But it's got to be a physical circle. So we could make the circle of my emotions work, but it would take a little bit of, it would take a lot of work. So picture a circle, any size, anywhere in the universe. Take a moment, and then let's get a few ideas. Okay, so if you would, did anyone here picture a circle that is smaller than this room? If you did, raise your hand. Okay, and wait, keep your hands raised, because I got Vanya, do you mind saying, and I'll repeat, what is your circle?
The base of a hat.
The base of a hat. Okay, so like the bottom of a hat is Vanya's circle. That's a fantastic circle. Go ahead.
Sure, bicycle wheel.
I'm sorry?
A bicycle wheel.
A bicycle wheel. Okay, so we've got a circle that is the shape of the bottom of a hat. We've got a bicycle wheel. Did anyone picture a circle that is bigger than the room? Yes?
The visible event horizon of a black hole.
The visible event horizon of a black hole. This is going to get interesting. Did anyone picture a circle that is bigger than this room that is not the visible event horizon of a black hole? Which totally works. Yes? Stonehenge. Okay, so the circle that kind of demarcates the bottom of Stonehenge.
The sun.
The sun. Wait, which part of the sun? Just.
On the corona.
Okay, so the circle that encloses the sun. All right, so we've got, the sun is a really interesting one too. Okay, so we've got all of these circles, and just carry that idea of your circle through what follows. I want to make a claim, a slightly complicated claim, about circles in the universe. And here it is. By antipodal points, I just mean points that are opposite each other. So if you draw a line from one point to the other point, you go through the center of the circle. So the claim is that in any circle, or on any circle, there are 2 points. There may be more than 2, but there are at least 2 points directly opposite each other where, and I just picked temperature. We could pick some other value, but let's pick temperature. Where the temperature of those 2 points is exactly the same. Now remember, this should work for any circle. So it should work for the hat, but it should also work for the hat if the hat is submerged in ice. It should also work for the hat if one side of the hat is touching the corona of the sun and the other side is not. It should work for the hat at every moment that the hat exists as you throw it toward the event horizon of a black hole. Any circle in the universe, the claim is that you should have a pair of points opposite each other with exactly the same temperature, even if one end of the circle is on fire. This is a complicated claim because we're making it about all circles everywhere, right? And you can imagine that if your circle is very big, if your circle is as big as the sun, as you zip around that circle, you're going to have so many temperature changes. And not only do you have to keep track of those temperature changes, but you've got to keep track of the temperature changes right across from you. And at some point, maybe, if the claim is correct, and I have not stated that the claim is correct, only that it's complicated. At some point, we're claiming that the temperature directly opposite you will be exactly the same. Just by a show of hands, who actually, remember, we haven't shown anything about this claim. Who actually believes it? If you do, raise your hand. If you do not, raise your hand. And if you are lost, raise your hand. Lost is a good place to be, I guess, as long as we understand what the claim is. Not whether it's true or whether it's false or how we would go about showing it. As long as we understand what the claim is. Now, I know that there's there's a bit for Q&A at the end, but I actually do want to pause for a moment just to make sure everyone knows what the claim is. So are there any questions about what the claim is? Yes?
Does time enter into?
Very good question. Does time enter into it? No. So I'm saying that at any moment in time, the temperature at one point and the temperature at the antipodal point will be exactly the same. Now this gets a little bit hinky when you're on the event horizon of a black hole because time there is, which is why we're going to leave that one just.
For example, submerging a dinner plate in hot water. So as this side is.
Yes, very good example. So if you take a dinner plate and you submerge it in hot water, if you freeze time at any moment, the claim is there are 2 points opposite each other that are the same temperature. At any moment. It's a complicated claim. It's a claim that I think most people in this room appear not to believe. Some people in the room are just confused by it, and some people believe. I want to try and take another look at it, though. So I have a prop. Okay, I guess I need this, so I'll put this down. I have a prop. So this is the frame for a tent. I want to make a circle in the room, so I don't just wave with my hands. Can I get 2 volunteers? Sure. I promise you will not be asked to do math. And I need one other volunteer. Yes, please. So it's Leticia?
Yes.
Leticia? And Gabe. Okay. Okay, this is live theater, so it could all go wrong. We've got to figure out how big our circle is going to be, because the 2 of you are going to have to move around the circle a little bit. Yeah, we'll make it work. Okay. I mean, I guess, so this is going to be the equator. Or, sorry, not the equator, the diameter of the circle. Leticia, you want to take one end, and Gabe, you're going to take the other end. All right. If this all goes sideways, I guess this is adjustable, so we could make the circle shorter. Okay, this is the dotted, look at that, it's got dots. This is the dotted line. This is the dotted line. Okay. So if you imagine a circle where this is the diameter, so this circle is going to go like that, and it's going to go around the room over there, and it's going to come back over here. It's going to go through Gabe, out the other side of Gabe, around there.
Am I in?
You're in, I mean, I'm not very good at judging distances, but I think you're just outside the circle. I mean, literally, not metaphorically. Okay, so it's going to swoop around that side, and it's going to come back to Laetitia. Okay, so everyone can picture the circle, yeah? Picture the circle. So the claim is that on that circle, there are 2 points, and if you want to, picture the sun at one side of the circle, or like a hot water, or imagine it's a really big hat. Okay, so the claim is that there are 2 points on this circle that are exactly the same temperature. Now, these 2 points might be those points. The point defined by Gabe, so Gabe might be a certain, not Gabe, because Gabe's going to move, but the point right here might be a temperature, and the point right here might be a temperature, and those 2 temperatures might be exactly the same. But that's not proving the claim, that's just getting lucky, right? So maybe they're not exactly the same. Maybe they're not. So, I was going to ask, let's imagine one is hotter than the other. But I'm not going to do that, because it's weird. So instead, I'm going to say, imagine we have, I don't know, someone give me a number.
3.14.
37. Okay, so, okay, we are going to have to do a little bit of math with these numbers, so don't make it too wild. So 37 and another number? 42. Okay, you made Gabe hotter. Okay, so let's imagine this point here is 42 degrees Celsius, say, and this point here is 37 degrees Celsius. So they're not the same temperature. In fact, don't answer out loud, just think about it. In fact, I want to figure out the temperature difference between the 2. That's the only math we have to do. That's one of 2 math things we have to do. So we've got 42, 37. Okay, so on the count of 3, I'll say 1, 2, 3, and then tell me the difference. Okay, 1, 2, 3, 5. Okay, look at that. And units. Okay, so we've got a 5-degree differential here. Imagine we have a 5-degree differential, 5 degrees hotter, 5 degrees cool. Okay, so these points are not the same temperature. But imagine now that we do this. Imagine that we take Laetitia and Gabe, and we rotate this just a little bit. So let's call this the 12 o'clock position. And this is going to be our 12 o'clock. Okay, so we're at the 12 o'clock position. You know what? This is going to be our 12 o'clock. Okay, we're at the 12 o'clock position, and the temperature differential is 5 degrees. If we rotate this, the temperature differential might be a little bit different, right? It might be, because Gabe might be a little bit different from 42 degrees. Laetitia might be a little bit different from 37 degrees. And if we keep on rotating, it might stay the same, it might be different. But what I want to do is I want to imagine, okay, everyone who is in the sweep here, you're going to have to kind of crowd surf this tent pole. Okay. Gabe and Laetitia, pass it over to someone. But stay where you are. Okay, so pass it over to someone, pass it over to someone. Yeah, and we're going to rotate. Whoop, whoop, whoop. Until, okay, now Gabe, you go at this end. Laetitia, you go down at this end. Okay. Now, my question is this. What is the Gabe minus Laetitia? Is that what I want? Yes. What is the Gabe minus Laetitia temperature differential now?
-5?
It's, who said -5? It's -5. It's -5. We have to imagine that we did that instantaneously, right? It's -5 because at this point, when Gabe was over here, this point here is 5 degrees hotter than this point here. So the temperature differential between these two is now -5. We went from 5 at the 12 o'clock position to -5 at the 6 o'clock position. from 5 to -5. And all the time, as we were rotating this, the difference of temperatures was changing. It may be in a mysterious way, but it was changing. But somehow, it got from 5 to -5. Okay. And to get from 5 to -5, you've got to go through 0. So that means that somewhere in that half arc, somewhere in that sweep, the temperature differential had to be 0. Somewhere between 12 o'clock and 6 o'clock, the temperatures had to be exactly the same. Okay, Leticia, thank you. Gabe, thank you. All right, let's give a hand to our volunteers. Thank you, thank you, thank you. So nice. So what is the temperature at these points? That's a complicated thing. What is the temperature difference at these points? That makes things much simpler. It goes from 5 to -5. If we had started with, I don't know, if the temperature differential had been 100, it would go from 100 to -100, and somewhere in between it had to pass through 0. Now I could stop there, because we've done some math, and that is the most important thing to me. But I want to take a couple minutes just to make a quick observation, the tricky fourth act. So in math, making something simple. No, let me take a step back. In math, simplicity is not a feature of a thing that is unchangeable. Right? Things are not kind of born simple or born complicated. Instead, simplicity is a thing that is rendered. It's a thing that you can make things simple by taking that lateral step, by taking that side step, by looking at temperature difference instead of temperature. And I think when we teach math, and maybe when you teach your thing as well, this is also the case. It's like our musician said in the intro to Sweet Moon, that sometimes it's about saying things or seeing things that are familiar in a different way. It's not temperatures, but temperature difference. And when we teach this subject, the job is often not to say, here's all this cool new stuff. Instead, it really is to say, just look again at the thing that you've been looking at. Try looking at it from here. Try looking not at temperature, but temperature differential. And now tell me what you see. Thank you.
First of all, thank you very much. That was very insightful. I'm curious how this works in 3 dimensions, because we talked about it on the 2-dimensional plane.
Yay.
Okay. So, because of the mics, I don't need to repeat the question. Well, let me repeat the question now.
Yeah.
Okay, so the question is, how does this work in 3 dimensions? Really, really good question. So if the question is, can we make a claim in 3 dimensions that if you have a sphere, that if you pick any, that there are a pair of points where if you draw the line through the points, it goes to the middle, that pair of points is the same temperature, you can still make that claim. In fact, you can make the claim that there are an infinite number of points like that. Because think about so imagine a sphere, imagine the Earth. It's not a sphere, but imagine it's a sphere. Okay. And then imagine the equator. So we just did this thing for the equator. On the equator, there are a pair of points that are exactly the same temperature. And now, I gotta watch my hands here. Okay. And now, I can define the shape of the Earth by taking this equator and kind of rotating it, right? And at every point when I rotate the equator, you're gonna be able to do the same thing. So that means that for all the infinite number of rotations of the equator that I do, you can always find a pair of antipodal points. Really cool question. So there are an infinite number of them, but can I leave you with one question? And this is a bonkers question. Is it, how should I put this? Can you find pairs of points that have the same temperature as you rotate this, such that they're connected? Because they might not always, right? We didn't say that if you rotate it, the pairs of points are gonna move like in a connected way. Can you do that? And I think the answer is yes. And there should be a name for that. They should call that a thing.
Did we just create a theorem?
Maybe?
Write it down on
Yeah,
the chalkboard.
great question.
Good. Oh, there you go. Now I'm a little worried if my question's too far, because Mark was making fun of me for it earlier.
Pass.
We can say pass.
Is this the circle theory that you discussed with us? Is that kind of like the basis for quantum entanglement?
Okay, so the question is it the basis for quantum entanglement? I don't know enough about quantum entanglement to be able to answer that question. But I will say that so underlying this theory is something called the intermediate value theorem and continuity, which I would bet all the money in my pockets. I have no money in my pockets, but if I had money in my pockets, I would bet all the money in my pockets that somewhere links up with virtually anything in mathematical physics, including quantum entanglement. Yeah, great question. Great question.
Thank you for being here.
Thank you.
You're talking about circles, and you know, with circles, usually pi comes out 3.14. And you did say there was a relationship. So does pi come in this theorem, or it's not significant?
Okay, so pi itself is not significant in this theorem because the circle is not actually necessary in this theorem. So, if you remember what I talked about, which, you know, but you can imagine doing the exact same thing with a shape that is not a circle. As long as you can rotate it, and as long as at any point during the rotation, the line only hits 2 points. So for the mathematicians in the room, this means that the shape has got to be convex, so it can't kind of loop back on itself like that. But other than that, you could do exactly the same. We could do exactly the same thing with the antipodal points with a sort of amoeba shape. But I'm happy to talk about pi. But with respect to what we did, you actually don't need the circle. It's a more powerful theorem than what we showed.
Can I put a question? Why do people think your work as a mathematician isn't creative? It's probably its own talk, but what happened along the way where you were put in the category of a non-creative professional?
You know, that is worth an entire talk, I think. I'll throw to a wonderful essay by a mathematician named Lockhart. It's sometimes called Lockhart's Lament. So what happened is, I think to some degree, we as mathematicians, especially as teachers of mathematics, sort of messed it up. So in Lockhart's Lament, he imagines what it would be like if people taught music the same way we teach math. That in first grade, people would just go and write down ledger lines. And that would be your job. Write down ledger lines. Don't worry, we're going to get to the music eventually. But right now, you really need this technique of writing down ledger lines. And in second grade, you might start drawing notes and filling them in. And these notes we call quarter notes. And these ones with a little thing we call eighth notes. And these ones with two little things we call 16th notes. Don't worry about the music. We're going to get to it. All right? And only by the time you hit grade 11 or grade 12, when all of the potential joy of music has been taken out of it, at that point we would say, you know what? Now that you all know how to write your ledger lines, now that you've all spent half an hour every night on copying ledger lines, we're going to listen to some music. And of course, at that point, nothing's going to happen. I think so much of it has to do with how we teach mathematics, and so often we teach all the grammar but none of the poetry. Am I calling? No.
When you, we're going to go to the Zoom room next, because we've been very IRL dominant. So Zoom room next. Sumit's got the mic with the Zoom room. Okay.
Okay. So I've got, my name's Christine, but I'm asking a question on behalf of Amanda in the Zoom room. And she asks, how do you know you've simplified enough? And an alternate to that question, can't you pretty much simplify things infinite times? So when do you stop, I guess?
Wow, these are really tricky questions. Okay, so the first question, how do you know you've simplified enough? And the second, can you simplify infinitely? But I think that's more or less right. Thank you, Amanda. Okay, so the first question, I think generally is a prudential question, or a tactical one, let's say. So as a mathematician, if you're trying to show something, I guess you know you've okay, I'm doubting my answer already. I was going to say, you know you've simplified enough when the thing is simple enough to be able to work with it, and to show the thing that you want to show. As for whether or not things can be simplified infinitely, that's kind of that's a really deep philosophical question. Is all of mathematics kind of connected? Yes. The answer is yes. And you know what? That's worth another talk. But I want to take back my first answer a little bit. I said it's a prudential question. How do you know you've simplified enough? And I said you've simplified enough when it's simple enough to do the thing you want to do. I don't think that's quite true. There is a question here, not just of true things, but of beautiful things. And maybe even good things. Let me just dip a toe into that and leave it at that. There are over 100 proofs of the Pythagorean theorem that when you have a right-angled triangle, the length of this side squared is equal to the length of the shortest side squared plus the length of the other side squared. There are over 100 proofs of this. Now you would think that if what you need to do is show that this is true, one proof is enough. But why do people keep on coming up with proofs of this thing that has been proven over 100 times? I think the reason is we're driven not necessarily to show that something is true. You know it's true. But instead to show that it's true in an interesting or lovely or beautiful way. If you think about kind of music and poetry again, it's not as though the first time you see Romeo and Juliet, you think like, okay, so I've done tragic love, right? And there's nothing else to say about the subject. I think we say things about the subject not just to reveal truths about the subject, but to reveal truths about the authors, and to reveal lots of things. So there's something more than prudence. Okay, I didn't really answer the question, but it's a great question. Thank you, Amanda.
Woohoo. Okay, our next question, and stand up, say your name, and then deliver the question.
Hi, I'm Shiraz. I'm also a mathematician and a medical statistician. My question is about teaching mathematics. it seems a lot of people get frightened even before the first lesson. How can mathematics education be simplified? And second is, during the COVID, there was a lot of teaching through online. So do you think the electronic and all the gadgets we have, does it simplify teaching of maths? Because we moved from chalk and stick to screen. Thank you.
Thank you. Okay, so the first question about how we can make mathematics less frightening? Less frightening. If you knew the depths to which some of my student evaluations of teaching descend, you may realize that I'm not the best person to answer that question. I think something can be. I'm a little bit wary of putting this on permanent record, but let me put it on permanent record anyway. I think something can be frightening and sublime. And I think as long as it is sublime enough, then look, math is hard. And it's, as you know, it's technically tricky, and there's a lot of stuff. But as I alluded to in an earlier answer, it seems to me that what's important is to make the stuff seem worthwhile. Right? You know, so the analog extends. It's not, writing poetry, writing music is hard. It's not enough to just sit and emote, right? There's craft and there's technique. But I think if that's, if you can see at the end of it that it's worthwhile, that it's for something, then I think students are willing to put up with an awful lot more. The second question about COVID and kind of teaching using gadgets and electronics, I think, I mean, certainly I welcome all sorts of tools. And I think we all should. But fundamentally, it seems to me that teaching is a thing that people do together. You've got 2 people or 200 people or 2,000 people, but there's a connection of minds. And I guess I just think we mustn't lose sight of that. That an awful lot of good teaching was done with people drawing figures in the sand with sticks. So we can do more than that, but we don't always need to do more than that.
We'll have time for one more question. Sumit, over to you. You pick someone. Someone on this side of the room, because I've been hogging on this side.
Thank you. Thank you so much for bringing to light about the teaching of mathematics, because I'm a huge believer that we need to make it far more interesting for young people, okay? My question today, and about a plug for the Khan Academy. So to your answer, sir, you know about the Khan Academy online? It's free mathematics. You can learn anything, simply, okay?
And your name?
My name is Kathleen,
Hi,
also with a K, Khan Academy, also with a K. I have a 3D printing company. We're doing research in that field, but my question to you today is on simplicity, and that is, could you speak to us just for a moment about the quality of 0? So we talked about 0 and 5 and -5 and differentials, but let's just do a little minute for 0, which is not a number, right? It's a quality, infinite and nothing, infinite and nothing, something like that.
I don't know if this is going to be an alley-oop or we keep going. You were
Okay, it wasn't a setup. In fact, I'm a little bit frozen. But let me try and connect it back to the notion of simplicity and creativity. This is one of those moments where I think in the future we're going to have this thing where I can kind of look a certain way, and then in my glasses the relevant Wikipedia entry is going to come up. But okay, 0 is a number. 0 is a number, but it is in some sense an invention. So what I mean by that is that I think there's a portion of the history of mathematics in a bunch of mathematical cultures that that function without zero. But or they didn't function without zero, but they function without zero as a symbol. And the introduction of zero as a symbol, I think, so one of the early adopters of zero was kind of Arabic mathematicians. And the immense power that gives you to do things like algebra, itself a loan word from Arabic, is astounding. So to think that you've got the symbol that stands for nothing. And simply like incepting that symbol opens up an entire branch of mathematics that will now kind of abide forever. That's pretty wild. Yeah, thank you.
Thank you. Woo! All right, stay for a second.